Thanks everyone for attending. So yes, I'm working on the audio-based toxic language detection here. As Demetria mentioned, I'm a final year PhD candidate at UT Dallas, and this summer I got the opportunity to join audio and acoustic group to do this project as the audio-based toxic language detection. So we know social networking platforms are very popular nowadays, but also research shows that interaction between people on these platforms naturally leads to aggressiveness and hostility. So it's good that we can find a way to control this toxic behavior or negative behavior that might happen in any of these social platforms. So toxic behavior could include cyberbullying, cyber threats, online harassment, or hate speech. But since each of these terms are indefinable and they could change from situation to situation, each platform has its own policy to control the toxic behavior. So in this project, we focus our attention in online gaming community, and we know that there is some elements in online gaming networking apps that make it more toxic, makes it a more toxic environment. For example, there is this competitive element that a huge group of people would come together and they would compete to win a competition. So that would increase the toxicity level of the game. And also the research shows that the higher, the more toxic you are in the online gaming society, the higher rank probably you will get in the competition. So the toxicity is part of the game. We cannot eliminate it from online gaming. We just want to find a way to control it and to avoid the extreme level of toxicity. So I have included some literature review in the slide to mention 3 very important points. So there are a lot of work on cyberbullying, hate speech, offensive speech, and sentiment detection. We can definitely leverage this finding to design our own system, but none of these systems are directly applicable to our task because they only cover one aspect of toxicity. And then the second point that I want to mention is that most of the system work with text, and they are text-based because they usually want to find toxic comments on Twitter or Facebook or YouTube. So we find very few studies that work on audio modality only. And also the third point that I want to mention here is that, for example, in this work that is sentiment detection and uses text, audio, and video, they still get very low performance, and that's mainly because the nature of this problems is very subjective, is undeniable. Even people and human may disagree on the sorry, excuse me, I'm facing some problem on the nature of the definition of the problem. So therefore, we decided to do the audio-based toxicity detection just to, and our motivation to do this was because we know that naturalistic and noisy data might affect the performance of the ASR, and it could be it could give us incorrect transcription, and then the ASR system is not always available. And then there are some cues in the acoustic of the WAV files that can be lost in the text, like pitch, tone, and some emotional cues that could help us to detect toxicity. And our perspective here is to reduce online negative behavior in gaming community, and also to decrease the workload for the human moderator that actually has to sit there and listen to every reported incident to decide if it's toxic or non-toxic. So with this introduction in mind, we are working on an internal private data set here in Microsoft for this project. And I'm showing the statistic of this data. So there are three categories in this data set: toxic, non-toxic, and debatable. And as you can see, debatable is a category that even the human moderator cannot decide if it's toxic or non-toxic. And the duration distribution of the data is depicted in this figure. And as you can see, 20% of the data is between 14 to 15 seconds long. But the rest of the data is somehow uniformly distributed between different durations. And then we have also visualized the words that are used, that have been used in the toxic and non-toxic categories. And as you can guess the words here, you would see that the words are almost the same as in these two classes, and we can infer 3 points from this. The first one is that toxicity does not really rely on the word. Maybe it is more relatable to the whole context. Sometimes a swear word is used, but the content is not toxic. And the second thing is that maybe there are some incorrect labeling that is totally understandable, because this is a huge data set and that's a lot of work that's a high expectation to expect to have correct labels for every example. And also the challenges that we face here in this data set is that we have weak labeling due to the strict user privacy policy. Each utterance comes with only one label, that is toxic or non-toxic. We don't have any information about the speaker's identity. And then there are very various background noises, music, reverberation, and overlapping speech, different microphone types. And the most challenging one is we have different languages in this data set, which makes it very hard to distinguish between toxic and non-toxic class. And then generally, toxicity can be highly subjective, and it can change from one person, one situation to the other situation. And I've included some demos just to mention some of this challenging data samples, just so that you can get an idea how the data looks like. So this one that I'm going to play, it just contains unclear content. So the next one. This one is extremely noisy. The entire utterance is noise. This one uses a different language. And then the last one is entirely music. Just like I know you should. I cannot give.
Mitia, quick question.
Yes.
Those recordings, did they have an annotation?
Yes, these have been labeled all as toxic examples, but we can say that some of them, they do not contain speech at all. It's just noise or music, but they have all been labeled as toxic. Mm-hmm. Yes, and then so this is the data that we're working with, and our task is audio-based toxic detection. So mainly we can divide this task into two parts: the features and the classifier. And for designing the features, we should be we're looking to find toxicity information in the lexicon, acoustic, and emotion. And we can't rely only on one of these aspects, just because, for example, let's talk about the emotion. Cyberbullying usually happens with laughing, smiling, and making fun of other people. So we can't definitely say if an utterance is happy, then it's non-toxic. So we have to take everything into account. With that in mind, we're proposing to use this system, which takes the utterance and has like some input features, extract some input features from that. And then we use a CNN structure here in the middle to extract some higher level information from the emotion cues, from the acoustic and lexicon that exists in the input feature. And then once we have the higher level feature map, which looks like this, it has a time dimension, it has a feature dimension, we should be able to classify this. But we face a problem here, and that's it. And that is that we have only one label for each of these utterances. So we kind of have to do some aggregation over time axis so that we squeeze the entire feature map into a feature vector and then pass that feature vector into the classifier for the final decision. So the first thing that comes to mind is doing an average pooling over time. But this is not the best solution, and this is suboptimal, because let's take into account, let's consider this example that I have here. Congratulations. You have achieved a whole new level of stupidity. And this utterance is definitely toxic. And if we're taking the mean or the average over time, chances are we're going to lose the information of the toxic information that we have in this sentence, because we have so many strong positive words. Congratulations, achieved, new level. So taking a mean over time dimension hurts us a lot in classifying these utterances. Therefore, we need to pay close attention to those words and regions that contain toxic information. So with this in mind, we want to incorporate attention mechanism in our structure. So what is attention? Attention is basically just a fancy word for weighted averaging. But what makes attention so powerful and so successful is that it uses very complicated mechanisms to find those relevant regions and assigning reasonable weights to those regions. And different attention types have different mechanisms to find those toxic regions. That's why we have so many variations of attention. So in this study, we just want to go back to the very basic definition of attention and just like introduce the terminology in attention in general. So in attention mechanism, we have three very important words: query, key, and value. To introduce these words, I'm using a very simple example like Google search engine. So let's assume that Google search engine has a database for eyeglasses, and each object is saved by a pair of key and a value. And then let's assume we have a person that wants to search for a specific kind of eyeglasses. So this person has a query, for example, oval eyeglasses. What Google search engine does is that it takes the query and it compares with the key of every object that it has in the database. And if the key matches the query, then it returns the value for the user. So in this case, because oval has the most similarity with round, the output would be the value of the round eyeglasses. But if the user is using a bad query, like tall eyeglasses, Google would probably either return something random or does not return anything at all, just because that query does not match any of the keys that we have. So this is what attention does. Basically, if I want to define the query key and value for attention, I would use the same feature map that we have and we extract from the CNN. Our goal is to find a region that is toxic. So we should define the query as a pattern that we aim to find in the feature map. And that pattern should be a representation for toxicity. That's the information that we're looking for in this utterance. And then we have a key and a value for each time step so that we can compare the query with the key, and if it matches, we are returning the value with a higher weight. here in our processing pipeline, we are replacing the average pooling over time dimension with an attention mechanism. And we are defining the key, query, and values here for this attention mechanism that we have. So for defining the key and value for each time step, what we do is that we take the feature map and we project it into two different spaces. We call one of them key, the other one value. And then we do this projection by multiplying the feature map into a trainable matrix, which can be considered as a fully connected layer. And also for the query, we have a trainable tensor. It's a vector. So we hope that the network is smart enough to learn a representation for toxicity during the training process. Just an important point to mention here is that the query is just a vector that represents toxicity. And it's used to find those toxic regions in the feature map by being compared to the key of that region. So the way attention works here is that we grab the query, which is only a vector, and we compare it to the matrix key that we have. So our key is a matrix because each time frame has a key for itself. So once we define the similarity between query and key by the dot product between this vector and this matrix. And then we apply the softmax activation function to get the alpha I, which is the attention coefficient. So if the query and the key have high similarity, then the softmax would be closer to 1. It means that we're giving higher weight to the value of that key because we believe it contains toxic information. And then, so once we have calculated this alpha I, which is the attention weight, we finally are able to get one attention coefficient for each time frame. So we multiply the feature map with this attention vector and we sum them over time dimension to summarize this feature map into a feature vector and pass it to the classifier. However, in this proposed method, there are two drawbacks. The first drawback is that what if the network does not learn a query that is related to the toxicity? And the second drawback is that even if in the best case scenario, the network learns a representation for toxicity, it only looks for toxic information and it does not connect the whole information that exists in that utterance, because sometimes we are using toxic information, but the whole content, we are using swear words and bad words, but the whole content is not toxic. So it's very important to incorporate all the entire knowledge that exists within that utterance. Therefore, we propose our second method, which uses self-attention mechanism. So in the self-attention mechanism, what we do is very simple. Instead of having a trainable tensor for the query, we derive the query from the feature map itself. So just the way that we projected the feature map into the key and value space, we project the feature map into another space, which we call it the query. It means that we use another fully connected layer to multiply on top of the feature map to get the query. So it seems like a very slight modification, but it actually changes the entire attention mechanism. Right now, our query is not a vector anymore. Our query is a matrix. So we don't have a single representation or single pattern that we're looking for. We are looking for a lot of information in the feature map. So what self-attention does is that for each time step, it defines a query, a key, and a value. So we have multiple queries here. And in the next step, attention considers every possible pairs of frame combinations. For example, if we are processing the first time step, we grab its query and we compare it to the key of every other time step that we have in the utterance. So we and then we calculate a coefficient, an attention coefficient for each time step. So for processing the first time step, for processing the first frame, we take into account all the relevant information that exists in the other time steps as well. This way, we're able to connect the information flow that happens to be in different regions of the utterance. So if I want to have the equation here, the mathematical equation here, we know that query is not a vector anymore, it's a matrix. So once we multiply it by the key matrix, we get a matrix for attention coefficients. So here again, the difference between this attention mechanism and the previous one is that now the attention coefficients is a matrix. Is not a vector anymore. And each alpha ij indicates how much we should attend to region J while processing region I. So therefore, this self-attention mechanism is able to capture the entire dependency and information flow that exists within that file without using any LSTM or any CNN networks. It does not rely on memory at all, but it can remember everything because it considers every region of the utterance for processing each region. So with having this attention mechanisms in mind, we are going to incorporate them in our baseline that we introduced earlier and to use them for audio-based toxic language detection. So right now I wanna, so in the next section, I wanna present our experiments and our results that we have based on our private data set. So here we are using the Microsoft internal data set. I'm referring to it sometimes as internal data set, sometimes as private data set. I'm referring to the same one. So we use the utterances that are between 4 to 8 seconds long. So we avoid processing very short utterances or very long utterances because they may be only noise or they may have a lot of silence segments that we don't want them. And then the utterances are chosen from toxic and non-toxic classes only. We are not working on the debatable class because this data have been labeled only by 1%, so the debatable probably is not very reliable, and even the human cannot decide if it's toxic or non-toxic. So it would be a high expectation if we are expecting a network to be able to classify them. And then we're using a threefold cross-validation technique to just verify our results with more confidence. And then we have 3 subsets for train, cross-validation, and test. We use 15,000 of utterances for the training set and 2,500 for cross-validation and for the test set. For the input features, we're using log MEL filter bank, which is calculated over 25 millisecond window with 10 milliseconds of frame shift. We use 512 FFT frequency beans, and we use 40 MEL filter banks. I just want to mention the reason that I use MEL filter bank over a spectrogram is based on my personal experience. They usually have the same performance, but spectrogram is 256 dimension, but this one has only 40 dimensions. So the processing time and the processing cost is much lower while using MFB. So this is the reason that I'm using MFB in this project. And then sorry,
can I ask a question?
Sure.
Between the toxic and non-toxic two sets, do you know what was the overlap in vocabulary, in content?
Yeah, so in the word cloud that I showed earlier,
I might have missed it, sorry.
Oh yeah, so it's just I'm not very comfortable saying these words, but all the swear words, the curse words, the words that we don't want to hear were present in both of them, just because, you know, toxicity is very subjective. For example, what might be considered as a very so what we use as a language with our close friend, which shows intimacy, might be toxic if we use in workplace, for example. So that's why both of them contains those words, but not all of them are toxic.
Medea, can you go back to that word cloud?
Thank you.
Yeah, sure. It's in.
One more.
So we have replaced some of those words. I hope you can guess, but so yeah, these are the overlapping words. And then so let's go back to the slide. So here, yeah, so these are the systems that we're working on and we have our experiments with. So the entire processing pipeline looks like this. We extract some input features and then we have a CNN that extracts higher level features. And then we use 3 different techniques to squeeze the feature map into the feature vector and we pass it to the classifier for a final decision. However, in the baseline, we just do conventional average pooling over time. So it's just like we're averaging over time, and that's the way that we kind of do the dimension reduction for the feature map. In the second system, which is the learnable query attention, what we do is that we learn a query and we search for those toxic regions, and we only pass the toxic regions into the final feature map, into the final feature vector. And then in the proposed method B, which is the self-attention, we kind of squeeze the entire content of the feature map without losing any information, and we compress it into the feature vector, and we pass that into the classifier. So we start tuning the system, the baseline system, and we use the exact same structure and hyperparameter combinations for the other 2 systems. So we did run a lot of experiments to find the best combination of hyperparameters, and we tuned the optimizer hyperparameters and the network hyperparameters, and I have shown this the binary cross entropy loss for the training and for the cross validation sets. And you can see that the losses are decreasing over epoch, and the network is definitely learning. And also there is no signs of overfitting here, and it's just like the whole training process is very it's going very smooth, and there's not any strange behavior in the training process. And with this, we evaluate the performance of those 3 systems with the private data set that we have. As you can see, we use different measures. We use accuracy, balanced accuracy, precision, recall, and F-score. So since our data set is imbalanced, accuracy is not very reliable. That's why we use balanced accuracy as well. Balanced accuracy is the same as average recall. So basically, we look into each class and we see that how many of the examples have been correctly estimated within that class. The precision is a metric that helps us to lower the false positives, and then the recall is a metric that makes sure that we can estimate the toxic utterances, and then F-score is the harmonic mean between recall and precision. And as you can see here in this figure, the accuracy and balanced accuracy for these 3 systems are shown. The learnable query attention and the average and the baseline, which is like averaging over time, has almost the same performance, and it just confirms our guess in the beginning that probably the network is not able to find a toxic representation, a toxicity representation, because of its nature, because it's indefinable and it varies from situation to situation. But we can see that the self-attention mechanism outperforms the other two systems, and the amount of improvement is not clear here. That's why I have included the table as well. We get almost 5% improvement in accuracy, balanced accuracy. We get 6% improvement over precision, and then recall also improves by 1%. And I have also included the standard variations of the 3 experiments that we ran, because we're doing the 3-fold cross-validation. And the standard deviation is very low. It's almost less than a 1%, around 1% for different, it's different for different metrics, but it's usually around 1%. So it's a very good sign that this networks have the same performance over different subsets of the data. And we also plotted the ROC and precision recall curves for these 3 systems to be able to calculate the area under the curve. So the higher the area under the curve, the better classifier it is. And we can see that the green light here, the green line represents the self-attention mechanism. The red one represents the learnable query attention, and the blue line represents the baseline. And here again, the self-attention outperforms the other 2 systems in terms of the ROC curve and the area under ROC curve. And also in the precision recall curve, we can see the same pattern of results. Self-attention again outperforms the other 2 systems, and it has higher area under curve. So with this evaluation, I was curious to track down the misclassified samples to see if we can find any interesting observations. So we have 2 classes for the false estimations. The first one is the false positive, and the second one is the false negatives. So the false positive are those utterances that have been incorrectly labeled as toxic. So I think I put it the wrong way. So we have estimated them as toxic, but the label says that they are non-toxic. A huge amount of this cases were due to incorrect labeling, because when I went back and listened to those utterances, I found that they are very toxic, but they have incorrect labeling, and the label says non-toxic. So they have been classified correctly, but because the tag is wrong, then they are counted in the error, in the final error. And then there are some examples that we have swear words in the sentence, but it's not a toxic sentence. It's just like 2 friends talking to each other using a swear word. And then another one that I found interesting was that the cases that we have a different language, we tend to have false positive on those cases, because some of these words that are in a different language, they may sound like a toxic English word, but I honestly cannot give my opinion on this, because I didn't understand if it was toxic or non-toxic. And I assume the network cannot be smarter than a human. So just as I cannot classify that, probably the network is not able to classify that as well. And then also the false negative class, most of them were due to some utterances that they do not contain speech at all. They're either, the whole entire thing is either noise or music. So I believe it's better to remove these utterances from the data set. And then again, severe background noise and severe background music were contributing to the false negative estimations. And then So in this slide, we kind of visualize the features that we have extracted with using the structure that we have, the proposed systems. I have used two methods to do the visualization. I have used PSA and TSNE. And as you can see, the first column shows the input log MEL filter bank, which you can see that for both toxic and non-toxic class, these features are overlapping and they're not distinguishable. So it conveys that log MEL filter bank by itself is not a good feature to detect toxicity. But once we use the self-attentive CNN to do the feature extraction, we can see that the self-attentive CNN pulls those features from each other and make them more separable. So it's much easier for the classifier to distinguish the toxic examples here. And we can see the same pattern of results with both PCA and TSNE as well. So now that we have all the evaluation that we wanted on the private data set, we thought that it would be a good idea to use this proposed systems into and use them for a public data set to see how the performance will change. And we use the IMOCAP data set, which is used for emotion recognition. It's a 12 hours of data. It has audio, video, and text. We just use the audio. And it has many different categories for emotions. And then since we were doing a binary classification, we had to make a subset of this IMOCAP dataset to use in our task. We defined a positive class and negative class. We combined happy and excited categories to form the positive class, and we combined the angry and frustrated categories to form the negative class. We do 5-fold cross-validation here, and our training set contains 3,000 utterances, and the cross-validation and test set contains almost 300 utterances. So this data set is very different with the private data set that we used earlier, just because the first data set is very large. It has large number of utterances, but it's very noisy. But this data set is clean, but it doesn't have that many utterances. So we thought that maybe data augmentation would be helpful with this data set because it's clean and it's very small. So probably augmenting it with extra data would benefit us. But we assume that for the private data set, we don't get much benefit with data augmentation because it's already a large data set and it contains every kinds of noise. So we are using this data augmentation called SpecAug, which has been introduced in the literature. And what it does, it simply masks some information in random frequency channels. We use this data augmentation on both the private data set and on the IMOCAP data set. And as we guessed, the performance on the private dataset does not really change. It's almost the same, but the IMOCAP dataset, it boosts the results by 3 to 14%, depending on different classification metrics. And then here is the final results of our proposed systems and baseline on the IMOCAP. As you can see, the self-attention mechanism improves the baseline by almost 2% over the baseline in all classification metrics. But for the precision, the learnable query attention has higher performance compared to the self-attention one. But in general, it just shows that this attention mechanism that we're using depends on the data and on the task that we're solving. And it definitely is a better option compared to just like average pooling over time. So with this, I want to present my conclusions and my contributions in this project. So we focused on developing audio-based toxic language detection. We designed a meaningful audio-based toxic toxic language detection system here. And then we proposed 2 different attention mechanisms to be incorporated into the baseline. And then we showed that learning a representation for toxicity is very hard because of its indefinable nature. And then we showed that self-attention can capture the entire content of the entrance, and this helps with increasing the classification performance by 5% absolute improvement, resulting in almost 76% accuracy. And we evaluated all proposed methods and all proposed models on both private and public data set, and we studied the effect of data augmentation on classification performance for both public and private data set. So this is what we did during the summer in audio and acoustic group. So before finishing my presentation, I would like to take this moment to thank everyone in Microsoft and thank Ivan for giving me this opportunity to be a part of audio and acoustic group. It was such a great experience for me, and I have learned a lot. I have expanded, and it really contributed to expanding my experience and my knowledge. And I want to thank Demetria for her great mentorship. I have enjoyed working with you, and honestly, it never felt like mentor and intern. It just felt like 2 teammates working really hard on this project. And thanks everyone for attending my presentation, and I would like to answer any questions if you have any.
Thank you.